It's Thursday, the 9th of June 2022, and welcome to a special feature-length water action platform where we're doing a deep dive into advanced anaerobic digestion, the pros and the cons. To avoid last-minute technical challenges, we usually pre-record these broadcasts just before going live, but today we are delivering this absolutely 100% live. Now, this is to enable you, our lovely audience, to participate in the Q&A at the end of the main broadcast. So if you have a question or a comment, please click on the purple triangle to the right of your screen and follow the prompts. Our program today includes interviews with operators, contractors, investors and suppliers, and I'm also delighted to say that I will be joined live from the US, where it is currently the middle of the night, by the technical director from Cambi, Dr. Bill Barber. We will also hear how operators can best manage the extra biogas generated through advanced digestion, or indeed what they could do to sequester the carbon dioxide that's generated alongside the valuable biomethane. Or what about all that extra ammonia that will inevitably appear because the more you digest, the more ammonia you create? Is it a problem or is it an opportunity? But before we get into any of that, let's start by addressing the basics. What is advanced anaerobic digestion? In fact, let's start with what is anaerobic digestion. Forget the enhanced bit for a minute. In simple terms, it is the natural breakdown of organic matter in the absence of oxygen. Organic matter is anything that's come from plants or animals and includes sewage sludge, food waste and agricultural wastes. A simple way of thinking about it is the bacteria eat the organic matter and in doing so produce a gas called biogas, which is rich in methane and can therefore be used as a renewable fuel source. There is a solid part left too, and that's called digestate or biosolids, and it's rich in nutrients. Anaerobic digesters are basically big mechanical cows converting organic matter into methane-rich gas and a nutrient-rich fertilizer. Anaerobic digestion is very popular across the water sector because, as well as producing biogas, it reduces the amount of solids requiring disposal. What is not to like? Well, brilliant though they are, anaerobic digesters are relatively big facilities involving potentially complex biological reactions. There are multiple stages in the biological digestion process, as shown here, and getting them right is key to running a successful digester. In particular, understanding and managing the rate limiting step is crucial, and this is precisely where advanced anaerobic digestion comes in. So with that in mind, let's now go to our first external segment from Dr. Bill Barber, Technical Director at Cambi. We'll hear from him live a bit later, but here's a message that he recorded last week after I asked him to talk us through what is advanced anaerobic digestion.
Hello, and today I'm going to talk to you about thermal hydrolysis and what it is and what the need for it is. But in order to understand the need for thermal hydrolysis and how it impacts anaerobic digestion and also other wastewater treatment infrastructure, we need to understand the origins of anaerobic digestion, and for this we need to go back in time into the 19th century. In those days, treatment was by cesspits and poorly constructed sewers. Disease was rife, notably cholera. There are outbreaks in 1831. In 1849, as many as 2,000 people in London alone were dying of cholera, and in 1854. Now, at the time, the main theory was that this was caused by a smell. This smell was known as miasma, but there was a doctor, John Snow, who had a theory it's more likely to be caused by the ingestion of food or more likely water. In the end, his theory proved to be right, but unfortunately he died before he could notice that. Meanwhile, in London, there was something known as the Great Stench. These runoff from these cesspits, along with pretty much everything else. Imagine the Industrial Revolution in the 19th century, slaughterhouse wastewater, industrial wastewater, breweries, these cesspits, pretty much anything else went into the Thames. That was a topic of debate for the notaries of the day, notably, for example, Charles Dickens, who wrote about it in some of his novels, Michael Faraday, who was talking about it, writing letters to the London Times. In 1858, there was a big heat wave. A lot of the water evaporated, and it caused this immense smell that was on everybody's nostrils, really. Everyone was sick to death of this smell. Parliament had built a new set of buildings on the bank of the river, and they were using ferric chloride to get rid of the smell. But eventually, when it affected the politicians and not before, because they'd been ignoring it for decades before. But when it affected them, they did something about it. They spent £3 million to introduce a sewerage system, and essentially this was the beginning of wastewater treatment in the UK. So a lot of wastewater treatment infrastructure was designed in the 19th century to deal with 19th century drivers. Anaerobic digestion is no exception. So if we look at digestion today, things like primary treatment, even things as like dewatering, everything we see in wastewater treatment today was built to 19th century drivers. But today we are in the 21st century. We're looking at water, energy, nutrients and carbon with the impacts of climate change, energy volatility, construction of megacities, growing populations. We are looking to conserve all of these things. Unfortunately, because the wastewater treatment plants we have today were not designed to conserve all of these things, they are fundamentally not efficient at water, energy, nutrients, or carbon conservation. And this is by design. Well, in today's drivers in the 21st century, we're looking at anaerobic digestion as a means of the production of a renewable energy as a methane-enriched biogas, which is the result of the disease destruction, which is why we have anaerobic digestion. So we can see here on this graph, this shows the production of biogas over time. If I have an extended period of time, I don't really need to do anything to the digestion system. But if I'm limited for space or time, then I have to do something. So imagine I have this graph here. I could put a pin in both ends of that graph, and then I can get my hand and I can stretch that graph out. So you can see it there stretched out to the left. This is what happens when we improve the hydrolysis process. Hydrolysis is one of the steps of anaerobic digestion, and as a rule of thumb, the harder something is to degrade, the more hydrolysis is rate limiting. So if I can enhance the hydrolysis process, I can get more biogas, greater performance of digestion in a shorter period of time. So there are many technologies which can do this. Some of these involve biological systems. Some of them involve physical systems when we break apart cells using some kind of physical way. Chemicals, I can use chemical lysis to destroy things, or thermal hydrolysis, which is what I'm talking to you about today. And thermal hydrolysis essentially is a pressure cooking system which uses temperatures in excess of 130 degrees C. To put this into context, 130 degrees C is in excess of the temperatures used by hospitals to sterilize equipment. And the reason we do this is to change the properties of the sludge in a fundamental way which impacts downstream processing, with anaerobic digestion, dewaterability, sterilization, increased loading rates. Subsequently, it's become a mainstream technology. We can see a graph of the uptake over time. The first plant was in 1995. There are currently about 130 plants in the world today, ranging in size from 5 to about 400 tons of dry solids per day, and it's become pretty much the pre-treatment of choice for anaerobic digestion.
Wasn't that great? I loved the historic positioning that Bill shared at the start of that segment. So now we've heard from the leading supplier of anaerobic digestion, advanced anaerobic digestion systems, but what about the operators? Do they share that same level of enthusiasm? Now, if you're an operator, please use the chat function via the purple triangle on your screen to add your comments. Advanced digestion has been used by Northumbrian Water for over a decade. They have two 40,000 tonne per year facilities treating all of the sludge that comes from their 4 million or so customers. So last week I spoke to Tony Rutherford, a treatment works manager in Northumbrian Water. Now, aside from being a very experienced operator, he also has a wonderful, rich Geordie accent. I asked Tony what he thought, what he liked about the Cambi installation.
Yeah, I mean, with regards to Cambi, and right at the beginning when we were commissioning the team ethics with the Cambi guys and the way that we commissioned the plant, it just works. And it's a fully contained pressurized system, which, specifically for Howden with sludge treatment and our proximity to local residents regarding odours from conventional sludge treatment, Cambi, like I say, it just works. And it made a massive difference to the process, to how we could put sludge through the plant, and we have a means there to treat it with, I dare not say it because I'll cause a breakdown, but we'll have minimal breakdowns on the plant.
Tempting fate.
I tempt fate there because, and credit where it's due, it just works. And, the amount of times that I've done a site visit to Howden and shown different people around, I call it the sexy bit of the plant. It really does work, but we need to look
at it. It's funny.
It.
I like the bit where you say, the kit that they supply, it sort of does what it says it's going to do. Yeah, because there was one of the first installations which was done in the UK. I think the water company, it was Thames Water. I think we can say that now that it's 25 years ago. And they thought that there was some of the kit that they knew better around, some of the sensors, and they kind of applied their own sensors to it. And it didn't work. It broke the process. So it's really interesting that you trusted that Cambi knew what they were doing, and they arrived and installed it, and it worked. That's the impression I'm getting?
It is, yeah. And I mean, I'm part of the Cambi User Group UK, and we share experiences with other water companies, and we come together and we talk about things that have worked really well, things that haven't worked so well. And I think it's just that understanding. It's the process itself and the actual the software, the way it works. However, we have made subtle changes to it over the years to make it even better.
All right, well, let's dig into those. But just before we get to that, the gas production, the big thing about Cambi is it claims it can sort of double your gas production or increase it by 50% plus. You've seen that, have you?
Yeah, for sure. It's a game changer really in the digestion process. We through our digesters, we're looking at probably a retention time of 16 to 18 days. We know that the Cambi process, it delivers, and we definitely, based on that type of throughput, definitely generate much more biogas than conventional digestion.
Okay. All right. Well, now let's move to talking about the cons. What's the downsides of Cambi? And you teased me there with a little mention of we've made a few little modifications. Can you dig into those? Are you allowed to share anything around those?
Yeah, sure. I mean, it's really looking at, originally we're talking about sludge feed times, the reactor blowdown times, so how that operates, really just to see how much heat that we could reuse and recover. So we did a couple of little changes on that, the timing on the software, just to say, rather than, delaying things, we'll try and contain as much of that heat and reuse it, and as an efficiency that worked really well. I think going into the cons, it runs flat out 24/7, 365, so the plant is always online. Every 2 years, as per our written scheme of examination for our insurance inspections, we'll have to take the plant offline. We'll have to do a lot of, the cleaning of the vessel, a lot of remedial work, holding spares and doing that change. And it's fine to plan that in, it's just, it's an additional thing that we have to do. And I think the upskilling of the guys, as you mentioned right at the start of the interview, Pierce, about the traditional sewage treatment work operator, where we're not that anymore, so a massive upskilling. And I think probably the biggest thing with it, when a Cambi installation is put in or a thermohydrolysis plant is installed, people often forget about the ancillary works around that, so the sludge feed to Cambi and what happens after Cambi, not to mention the boilers and the steam that we'll have to produce to put into Cambi, which required additional upskilling of guys with regards to operating industrial scale boilers. So probably the cons would be all of the things that have to work around Cambi to make it just happen.
There's a complexity that we're not used to in the industry, because we've tended to be a bit, in the past it's been turn a valve,
Sure.
And
Yeah.
that's how we've had to do it. What about the high temperatures and the high pressures and the health and safety side of things? Is that something that's caused you concern?
It probably did early days, and I think, again, getting the guys, the operators, the buy-in, especially with me being off, like classed as offline to work with the contractors, I was on that day in, day out. The buy-in of the guys, the health and safety, adhering to that, but the high temperatures definitely taking sludge samples thing. It's just taking a step back, risk assess it, and look at it, being a bit more pragmatic and really thinking about things like that and just taking the time to do it, so
And,
yeah, definitely.
And ammonia?
Yeah, so ammonia in the digesters, it's probably negligible about, the pros and cons against that, not going into the sewage treatment works and looking at the effect or the impact on the sewage treatment works and the energy that it takes to retreat that ammonia or to treat that ammonia that's left over in the process. I think it's the whole life of, looking at everything, not just at Cambi as in one thing, it's how it impacts the rest of the site.
Well, later in this broadcast, because you can't do advanced digestion without increasing your ammonia, because that's how the chemistry works. And people have often said, well, ammonia, that's a big problem for us. And it's interesting to hear that you're going, well, it's not such a big deal. But we're going to hear a bit later about how that ammonia can get recovered with organics.
Yes.
So I know you've got a history with organics, haven't you, in Northumbrian?
Yeah, so we're just starting our journey, I suppose, with looking at installing a pilot plant to see some of the technology that's out there and what we can actually do.
Yeah, in a beautiful bit of coincidence, we're going to be hearing from Andrew Moore, your colleague, but he won't have that wonderful northeast accent that I'm sure the audience is enjoying here. Tony, it's been wonderful to be with you. One last comment. On the balance of the pros and cons, where do they sit? If this was pros and that was cons, do they sit like this, like this? Where are you at with them?
Well, I've worked with Cambi for the last 10, 12 years now. And from my experience of being on the tools, working on the plant, and now managing the plant, the pros far outweigh the cons for sure.
I always find it wonderful talking to seasoned operators, especially when they know and love their plants as much as Tony does. Thank you, Tony. Now, Tony mentioned that one of the key benefits was the massive increase in biogas, which begs the question, what's the best thing to do with it all? Just doing more conventional CHP feels like a lost opportunity. Now, to help unpick what more could be done, I spoke to Colin Mills, Chief Executive of Future Biogas, a developer and operator of anaerobic digestion plants and, importantly, biogas upgraders. I started by asking Colin what the options were for all that extra biogas.
Okay, thanks, Piers. So traditionally, biogas from sludge digestion has been used and burnt in CHPs, combined heat and power units, which generally actually have quite a high level of maintenance and sometimes unreliable, which can result in extended periods of flaring. Also, some challenges around
the atmosphere.
Or venting, indeed. And some of those also are actually relatively inefficient in terms of a way to produce electricity. Around 40% can have some NOx or nitrous oxide emissions, and that's particularly challenging when those CHPs are located in urban areas. So really, there's a bit of a move and sort of, I suppose, best practice to be thinking, should we be actually purchasing green electricity from the grid instead of utilising CHPs for electricity? And what more and more technology, particularly over the last 10 years, has improved to enable biogas to be upgraded into biomethane or kind of natural gas, which can be injected into a national grid, whether that, if a geography has that, or compressed into road transport trailers, which can then either be taken for fleet filling or for, you can fill vehicles on site. So
and
really,
just to be clear, upgrading means removing the carbon dioxide and changing the mix from 60% methane up to 95% methane, correct?
Exactly, yeah. So there's effectively two prime products coming out of upgrading, the methane, and then, as you correctly say, the other one is CO2. And that, if the right technology is chosen with an upgrader, then it becomes possible to collect and capture that CO2. So
we'll come back to that in a minute.
Okay, so you actually have two prime benefits. One is financial and producing, a green gas for a premium. That's on top of potentially what the wholesale price is, and then also a greater contribution to sort of net zero by really letting others produce more efficiently green gas rather than burning it, and enabling the green gas to be used into the grid or vehicles for heat or fuel use.
And just walk me through the economics of the two of those. I'd love to hear your thoughts on the economics and the carbon benefits of the two different approaches.
Yeah, so in terms of pure carbon, the reality is at 40% efficiency, you're burning that carbon to produce green electricity. Against solar and and wind, they're much higher. So you've just got a built-in inefficiency. So there's a cost to that. And the reality is that there are OPEX differences and CAPEX, but CHPs without government subsidies are actually quite an inefficient way and quite expensive maintenance-wise to produce that green product, the product being electricity. Whereas an upgrader, there may be a difference in initial capital cost, but generally the maintenance is lower. Certainly the uptime and availability to produce green methane is much higher. And so the economics then in terms of waste is much improved, and actually putting it into the gas, and it does depend on the geographies whether there's sort of incentives, but certainly more and more industrial companies and big corporates are buying and paying a premium for green gas above the wholesale. So the economics are generally much improved for being able to inject either into a grid where it exists or to put it into road transport.
And it might be an unfair question, but if you were faced with, I'm bought into, I'm not going to burn my gas in a CHP engine. I'm going to upgrade it, remove the CO2. Which is better, gas to grid or road fuel, or is it so different on different localities it's not possible to give an answer?
Well, no, I think it's probably it will vary around geographies, but clearly if you have a grid that literally runs right past the utility site, it's probably going to be much more efficient to do that rather than invest in road vehicles to transport the fuel in a compressed state, which is actually quite expensive. It's at the end of the day, it's a compressed gas rather than liquid, so you don't really want to transport that by road. The economics quickly become less favourable then.
You mentioned earlier, you teased earlier with saying there were two products. There's the methane and there's the CO2. Now, I happen to know that Future Biogas is doing something quite revolutionary with the CO2 in the North Sea. Can you just give us the 1-minute version of what you're doing in the North Sea?
Sure. So that's a really exciting opportunity for Future Biogas, where we're working with Northern Lights project, which is a partnership between Shell, Total Energies and Equinor to sequester CO2 into the North Sea. Backed by Norwegian government, but the concept from Future Biogas perspective is that we will build subsidy-free anaerobic digestion plants that produce green gas and carbon dioxide. We've secured land at a port location in Hull in the UK, which we will be building a CO2 storage terminal. We will aggregate CO2 from the various sources and bring that to that location. It will then go by ship over to Norway and for sequestration into the North Sea. That's also an opportunity initially in the UK for others, including water utilities, because with the right technology, as we sort of discussed, you can displace a CHP and put in an upgrader, but there's also an opportunity for those who've already got an upgrader that perhaps vents CO2 to the atmosphere to put in what we call a bolt-on unit, which effectively ties onto the back of the existing upgrader where the CO2 might go to the atmosphere. It now will be going to be captured. And so from a sludge derived CO2 market today, there's not a lot of opportunities because it's not seen as acceptable in food and beverage. You need an industrial user, located nearby to present some challenge. So there's a big opportunity there where there is sequestration to actually, become negative carbon for that sludge. I
was about to say, forget getting to carbon net zero. This is getting to carbon negative. It's absolutely phenomenal. When do you think you'll have the first injection?
So we're looking at back end of 2024, early 25 to inject. So
fingers crossed. Really wishing you the best with that fantastically exciting project. Colin, thank you very much for your time today.
that's great. Thanks, Piers, and yeah, good to see that you joined us in your pajamas.
Now that was cruel, don't you think? Thank you nonetheless, Colin. Future Biogas are a leading biomethane operator, and as you saw there, they can also give you fashion tips. Joking apart, Future Biogas's ability to sequester or lock up the carbon dioxide is a really exciting development, which could make advanced digestion not just net zero, but genuinely carbon negative. So we've now heard what you can do with the extra biogas, but what about all that extra ammonia? Is it a problem or is it an opportunity? Recovering the ammonia rather than expending lots of energy destroying it, as we normally do in wastewater treatment, surely must be the sensible answer. But is it really possible to recover ammonia at scale and economically? Well, here's a contractor, Organics Limited, talking about what they have done to crack this problem.
Hello. Organics has been removing ammonia from wastewater since 1998, when the first facility was commissioned in Hong Kong. At the time, this unit, shown here, in a single footprint of 12 meters by 12 meters, removed as much ammonia as all the aerated lagoons treating leachate in the UK. It was rated at approximately 12 tons ammonia removal per day. Despite pilot plant trials and high-level design input, there remains some uncertainty about the efficacy of the process. Indeed, if the truth be known, the question was, would it work at all? It was a great day when it was finally fully commissioned. Since that time, Organics has built a further 16 ammonia removal facilities in Hong Kong. The technology has proven itself repeatedly. With the first installation, the requirement was to remove ammonia, destroy all of the ammonia so removed, meet a 100 milligrams per litre discharge consent requirement, and to use as much landfill gas as possible. That's correct, as much landfill gas as possible was to be utilised. That meant that the thermal efficiency was not a performance criterion. In 1998, biogas in Hong Kong was not a valued waste stream, and ammonia was cheap. In the years that followed, this baseline position gradually changed to where we are today. Biogas is highly valued and ammonia prices are increasing, recently in a dramatic fashion. To meet this challenging and changing commercial environment, Organics has invested in energy conservation as well as technologies for the recovery of ammonia. Ammonia may now be obtained from a wastewater ammonia removal system as either ammonium hydroxide, being ammonia in water up to typically 25 to 28%, and ammonium ion salt, such as ammonium phosphate, or as a pure ammonia liquid stored under pressure. The process as it is packaged now is suitable for almost any high-strength ammoniated wastewater, including THP side stream liquors, AD concentrates, landfill leachates, and various other forms of wastewater. The system uses waste heat, produces low greenhouse gas emissions, requires no chemical additions apart from anti-foam agent, and, not being based upon bacterial activity, is reliable and predictable with removal rates of up to 98.5%. As a general rule, the higher the ammonia concentration in the wastewater stream, the better the overall performance. Other important aspects of the process include a relatively rapid startup and shutdown, typically 1 or 2 hours. It is easy to operate and maintain and can be looked after by trained mechanics or electricians. It also typically has a small footprint. The process consists of 3 columns: a column to remove the ammonia from contaminated wastewater, a column to recover the ammonia, and a column to concentrate ammonia in clean water. with concentrations up to a maximum of 28% ammonia in water. If required, it is possible to take the concentration higher, up to a pure ammonia gas. Pure ammonia can be held as a liquid at ambient temperatures in a vessel rated at 17 bar pressure, or stored at a temperature of circa minus 33 degrees centigrade. There are, however, constraints to the applicability of the process. The alkalinity must be above a certain minimum concentration. The suspended solids must be managed to prevent blockage of column packing. The main constraint, however, is that there must be an adequate source of heat. Preferably, this would be waste heat. Biogas and landfill gas may be employed, but the use of primary fuels such as natural gas, propane or distillates make the process commercially unattractive. The days of waste fuels having no value have long since passed. Organics is currently delivering 2 pilot units to water companies in the UK. The first, the Northumbrian Water's Howden wastewater treatment plant, treating return liquors from a Cambi THP system. Part funding for this project has been supplied to Northumbrian Water-led consortium under the first round of Ofwat's Innovation in Water Challenge competition. The balance of funding is coming from organics. It is due to be commissioned in the third quarter of 2022. This unit will recover ammonia as a pure liquid and crack the liquid ammonia to create hydrogen. Here we are working in conjunction with the Wood Group, Cranfield University and Warwick University, who will do the catalytic cracking. Second unit will go to Severn Trent Water's Spurnal wastewater treatment plant, which will use a range of imported effluents. Part funding has been supplied under the EU Horizon 2020 programme, REWAYS, Resilient Water Innovation for Smart Economy. It is due to be commissioned in the fourth quarter of 2022. With the critical importance of ammonia to agricultural production and the price of ammonia rising dramatically, every opportunity for commercial ammonia recovery should be investigated.
Well, it's common sense, surely. Rather than destroy the ammonia, let's recover and reuse it. Now, the interview with Tony at Northumbrian Water earlier in the broadcast mentioned that they were looking at doing some clever things. Now, without wanting to go down a rabbit hole here is literally just 90 seconds from Andrew Moore, again from Northumbrian Water, talking about their innovation project on potentially cracking the ammonia to produce hydrogen. And don't forget, if you've got any questions, add them to the chat or give a thumbs up to other people's questions if you like them.
Thanks, Piers. We're going to install a organics ammonia recovery plant on the site at Howden to then take that ammonia and crack it to hydrogen. As you know, the sludge liquor return, the centrate off the digestate, is a really valuable resource, and it's where the ammonia is concentrated. And it's much better to try to recover that ammonia than pass it forward to the activated sludge plant, where it puts a load on the activated sludge plant, a very significant load. And again, I think much better to try to recover it rather than treat it, because as you'll know, if we were going to treat it biologically, we'd be producing nitrogen at best and nitrous oxides at worst. So producing ammonia and hydrous ammonia, and then hopefully cracking that ammonia to hydrogen will be absolutely super. We are sort of agnostic as to whether we go all the way to hydrogen, but obviously hydrogen is supported by the government's RTFO scheme at the moment, and that provides an additional cash stream. I think the project's going really well, and I think the issue will be around the energy balance and the opportunities perhaps to use waste heat from the Cambi process in conjunction with the organics plant, because as with all of these things, the energy balance will be key.
The energy balance will be key. That's basically saying that the economics for hydrogen cracking won't work without some clever thinking, which isn't too surprising. This rather nicely leads on to the next topic. So we've talked about the operational challenges associated with operating high pressure, high temperature equipment, and we've talked about the biogas, and we've talked about the ammonia. But what about the funding challenge? The payback might be great, but what about that upfront capital investment? Well, fortunately, there is a solution. Water Asset Developers is an organisation which provides third-party finance to water utilities to help them install bioresource facilities in particular, things like Cambi. Water Asset Developers is headed by Jean-Michel Herrewyn, formerly a senior executive at Veolia, and here he is sharing a little bit more. Jean-Michel, it's wonderful to be with you today. Thank you for taking the time. Now let's jump straight in. Utilities who are doing bioresource projects, in particular around things like Cambi, often struggle with how they can finance these assets. I understand you've got a solution that could help them. Can you tell me a bit about that?
Sure. The basic idea is to attract private money in financing this biosolid assets, generally speaking. This private money is coming from infrastructure fund, so people who are basically interested in long-term investment in physical asset, predictable and visible cash flow in a nutshell. And of course, everything today related to environment, water especially. Also with this energy angle that you will have with biosolid treatment and biogas production, I think is attracting a lot of attention and a lot of interest.
And so if I've got this right, if I'm a utility and I want to build a new anaerobic digestion scheme, you can provide the funding that will enable me to get that project up and running. What do you need from me? What commitment do you need from me in terms of the scale of the project or the length of the contract?
Yeah, basically, also I was talking about long-term commitment, so you will have to consider an horizon of 20 years, 25 years, something like that.
Not unreasonable.
You're talking about physical asset, so of course it's double-digit million of euro or pounds. So I don't know. So like above 30, 40 million as a minimum.
Excellent. Which is typically what any sensible sized digestion scheme.
I guess so. Of sludge treatment line or biosolid treatment center. I guess so at the minimum. I think, and of course, this investor will want to make sure that he's got the right partner. So you mentioned a very well-known technological company, Cambi. So this investor will, of course, team up with the right technical partner and also team up with the right service partner, because this investor will want to make sure that the solution he provides perform exactly conform to the, I would say, the plan, because of course his return will directly depend on the performance of the installation.
So it's about having a consortium with the money, the technology, and the right operating skills.
Absolutely.
Okay. And can you, just last question, can you tell me, are you doing this with anyone at the moment?
I mean, under confidentiality agreement that we have signed with a couple of potential clients. We are currently talking to two utilities located in Northern Europe. Sorry not to be able to be more precise, but we are entertaining absolutely concrete conversation. So with specific locations and also specific solutions. So we are there.
Brilliant. Well, I wish you well with that, and please keep us informed. Jean-Michel, thank you for your time.
Thanks a lot, Piers. Thanks a lot.
So, if you like the idea of installing advanced digestion but don't have the money readily available, let me know. I'll happily introduce you to Jean-Michel. Now, I have one last segment to share with you before we go to the live Q&A, and it's on what next for advanced digestion. 25 years ago, thermal hydrolysis and advanced digestion really was revolutionary. It's now becoming commonplace, 130 plus installations across the world. So let's go back to Bill Barber, Technical Director at Cambi, to see what he's got to say about the future.
So the question is, where will we go in the future with thermal hydrolysis? Well, if we look at the near future first, we're definitely seeing more and better data collection, monitoring of real-time trends both on-site and also remotely. This allows for proactive maintenance, spotting potential component failures and acting on them in real time. This will enable the plants to be more smoothly operated, extending the life of critical components, reducing the operating demands and costs of operation. We also see new configurations for redundancy. This is not so important in the UK, for example, where redundancy can be managed on a strategic level, but in other parts of the world where you may only have one treatment works, it's very important to be able to operate that 365 days of the year, 24/7. Along with those developments, we're seeing newer configurations for higher steam efficiency, which reduces energy demand for running the plant. So these are the kind of changes that we are seeing currently at the moment. But if we start taking our crystal ball and looking more further afield, it's difficult to say what the answer really lies, but there are some things we can be certain of. First of those is tightening regulations. The more we tighten wastewater treatment regulations, the more activated sludge and tertiary sludge we produce. These are the rate limiting step of the entire wastewater treatment system and can account for between 50 and 70% of the costs. So technologies which can treat activated sludge better are going to become more and more prevalent and more important in the future years. We are seeing now developing nations connecting to sewage sludge infrastructure. So we're going to see more and more sludge produced, not necessarily in Europe and the Americas, but more in Far East Asia, countries like India. China is investing heavily in infrastructure. We're going to see production of megacities, people moving out to agricultural areas, so we have far more sludge. We're going to see the impacts of climate change. Even if we stop consuming carbon today, these impacts will be there for years to come. So we need to build plants which are flood proof, have flood protection. We're going to see less water consumed, so quantity and quality of sludge in the future is going to be different. It's going to be more concentrated. So we need to take our existing technology and make it more suitable for 21st century drivers. But the problem with doing that, most of the infrastructure we have on site was designed to 19th century drivers. We designed digesters to control cholera from the outbreaks of the mid-1850s and beyond. So we're stuck with technology which was never designed to produce renewable energy in terms of digestion. So here we see a picture of a Ford Model T Touring from 1912. If you imagine anaerobic digestion, the design of that has not evolved since before that car was invented. So even with thermal hydrolysis, all we're really doing is putting go faster stripes on that car. It's still an optimized version of 19th century technology. Still a long way we can go. What we need to do is to challenge the textbook designs. If we want digesters to produce biogas, we need to start designing them to produce biogas and not for disease control. There's a lot of research ongoing looking at retention times, loading rates of anaerobic digestion, bringing these down, making them more affordable in smaller communities. So we need to challenge digestion, not just with thermal hydrolysis, but downstream as well. Thermal hydrolysis is complementary to all of these challenges of digestion. But going back to first principles, thermal hydrolysis was actually originally invented as a dewatering aid. There's a lot of work. Polymer, people don't realize that polymer is actually a large cost of running thermal hydrolysis system. So anything that can reduce polymer demand, or reduce polymer cost, will enhance the longevity of thermal hydrolysis. There's a lot of work looking at how can we improve the dewaterability even further. This you can do by increasing temperature. However, increasing temperature increases the production of melanoidins and refractory components. But there's ongoing research in Australia that shows that these materials can actually be extracted and concentrated at costs similar to that of producing fossil fuel fertilizers. So there's opportunities there. But potentially the answer isn't even anaerobic digestion. Whilst land application of digested biosolids cake is considered best practice environmental option, there may be options and scenarios where this isn't actually preferable or desirable. If we're looking here, we're seeing proteins, enhanced proteins being manufactured in China, which have a high value, which we're seeing a lot of interest now in future years. Instead of biogas production of proteins and other high value materials, we're seeing PFAS and other materials, microcontaminants, causing potential issues with land application of biosolids. So in these instances, they may rely on gasification, pyrolysis, hydrothermal carbonization, but all of those processes involve some kind of drying step. Where drying is involved, enhancing dewaterability, say by thermal hydrolysis, has a huge impact. So really looking forward, whatever the future may bring, by combining, say, thermal hydrolysis with digestion, we produce less biosolids of a higher quality, which minimizes risk, whatever the future may bring.
Brilliant. Lots to think about there from Bill. So let's now go to the Q&A session, and hopefully Bill can be brought live to connect to this broadcast. I do know that Bill's on the east coast of North America, where right now it is, I believe, just coming up to 3:30 in the morning. Bill, I've got this rule in life that you shouldn't get up you shouldn't work between at least midnight and 5 a.m. in the morning. I am right. It's coming to 3:30, isn't it?
Yeah, it's 3:15. It's not ideal, but for you peers, it's fine. You know, I have to say, watching your shirts in those videos, I'm feeling a little bit underdressed now. So, yeah.
Look, I get enough feedback on my fashion sense. Well, let's start with a minute on your background. Just tell the audience how long you've been with Cambi, what you did beforehand, all of that stuff.
Yes, so I'm currently based in North America, as Pierre said, on the east coast of the United States in Pennsylvania. I've been at Cambi working there since 2016. And prior to that, I was working for AECOM, and also I worked with Piers many years back at Atkins Global, so 2 multinational consultancies. I was living in Australia, setting up a biosolids business there. And previous to that, I was at United Utilities, where I was a sludge specialist, working with UU Water Company, the biggest in the UK, to develop what eventually led to the Davy Hume thermal hydrolysis project. And prior to that, I was in research, so I did my PhD at Imperial College in anaerobic digestion under the tutelage of David Stuckey, who in turn did his PhD in Stanford with Perry McCarthy. So it's sort of like the mafia of anaerobic digestion, if you will.
Cascade down, Perry McCarthy, David Stuckey, maybe Bill Barber will be the one that in 50 years' time people say, well, I knew Bill Barber. All right. I don't know whether you've been following the chat on the we've got half a dozen or so questions here, so if we could take a few minutes to just walk our way through some of them. Some of them might actually be just outside of your technical area, but let's see how we get on.
Sure. Fine.
So I'm going to go with the one that came from Marie. Which sludges work best for thermal hydrolysis? Primary, secondary, mixed? Maybe even digested. Sure. Could you do thermal hydrolysis on digested sludges? What would happen if we did that?
Yeah, exactly. So really, as a rule of thumb, thermal hydrolysis and similar technologies work best the harder something is to degrade. So if something degrades relatively easily, hydrolysis technologies really won't have much impact. So what we're looking at is increasing the biogas production in a shorter period of time, and this is the hydrolysis process. So we, like the graph I showed before, so secondary sludge is very difficult to degrade. That for me is the rate limiting step of all of wastewater management. It's high in viscous materials which retain water, so it doesn't dewater well. You have mass transfer limitations during a digestion process, so it doesn't digest well. So breaking that material up makes it more biodegradable. So in terms of municipal sludge, secondary activated sludge, the longer the sludge age, the harder it is to degrade. Looking further afield, if you look at other industries such as pharmaceutical wastewater, that's very difficult to degrade. So it would work well on that as well.
And it's difficult to degrade because I assume the fact that it's the high temperature and pressure, it's sort of breaking open the cells. And
exactly.
Pharmaceutical waste have that it's biological waste that's got thick cell walls or something like that, is it? That's
Yeah, so with biological wastewater, you have a lot of gelatinous material. So secondary sludge produces this gelatinous, viscous material as a byproduct of bacteriological metabolism. So it's that material that retains water like a jelly. So you can't really dewater it. It retains maybe 4 units of water per 1 unit of material. So you're never going to get really more than 20% dry solids there. In terms of industrial wastewater,
we've got a load more questions coming in, so I want to make
high
sure
molecular waste. Sorry, yes.
So, how much extra gas can I expect? I suspect that links to what type of sludges I've got in there, but how much? People talk about it doubling gas. Is everything from 50% to 100%? And how much extra gas?
Yes, I mean, that's, again, it's as you say, Piers, it depends what you're putting in the system, you know. But it's really safe. We're looking at primary sludge. That dewaters quite well already. Sorry, that digests quite well already. So you can say anything from maybe 5 to 15% more gas. If you've got a lot of activated sludge, which is difficult to digest, you can get maybe 50% or more gas. So it really depends what you have. But you can get maybe 50% more gas, I would say, for activated sludge.
And there's some logic in here. If I'm getting more gas, I must be getting less sludge.
Correct. If you're getting more gas, you're getting less sludge. And as we've discussed today in the videos, you're also getting more nutrients. So, you know, the more gas you produce, the more nutrients you release by default. So that's something that you need to address as well.
By nutrients, you mean the ammonia, obviously.
Yes, yes, absolutely, the ammonia.
Yeah.
Yes.
All right, an easy one, quick answer here. How long does it take to install a THP unit? Could you get one?
We've been working a long time on this to try and reduce the cost. So we have modular systems. So a typical plant, say 75% of plants will fit into something called a B6. That can be mechanically installed in a week on site. It comes pre-wired in 11 separate components. That could be operating within a couple of weeks of arrival on site. Excellent. So that's come down a lot in time.
And sorry, I was looking at the questions.
Sure, yeah, of course,
in terms of the pipeline, because it's a modular unit, most of it's made off site.
Correct. Most of it is made off site and pre-wired off site as well. So when it comes on site, it's just basic stuff, and then you're connecting it up to the utilities, of course. And then
set, isn't it? You turn up and it's like just building something with Meccano and Lego.
Yeah, pretty much. It's not far off plug and play. Absolutely, yes.
So linked to that, I'm going to go with Marietta Sandal's question here. Curious how big a THP plant can be and how small they can go. I suspect there's no limit on the upsize, but there must be a minimum.
Absolutely. So a lot of people think it's reserved for large technology, you know, for huge mega projects. But from our experience, there's only 5% of these plants that are in above 300 dry tons a day. So Cambi specifically, we have plants from anywhere from about 5 dry tons per day to about 410 metric. So that's quite a wide range of sizes there.
All right, I've got a great question here from Karen. How much research has there been on the destruction of PFAS through THP? And just for the audience's sake, PFAS are these sort of everlasting pollutants that we're seeing more of. Has there been any work on PFAS?
There has been work on PFAS, but as you're well aware, PFAS, these so-called forever chemicals, are intentionally designed to be thermotolerant and recalcitrant, so they're not designed to be broken down anytime soon. Hence the concern in the environment. There's been work, really anything you need some kind of thermal destruction typically to destroy those. Temperatures in excess of that used even by incinerators. So in that case, whilst thermal hydrolysis alone may not provide a solution there, when combined to other technologies which involve a drying step or some kind of thermal destruction, there's a synergy there because you improve the dewaterability, which enhances the energy balance because you have less water to extract.
Great. Thank you for that. So Wilfred has asked a question here that might not be one for you to answer, but I'm going to throw it to you. And if you don't answer it, Wilfred will get it answered by our friends at Organics. He says, on ammonia, we are looking at a watery stream with hydrogen sulfide and ammonia. Can these be separated into sulfur and ammonia? Any comment on that?
Yes, you can change the water chemistry in the digester. You can precipitate things out. If you add ferric, it has a very high affinity to precipitate out sulfur. So you can manipulate the pH. If you go to a higher pH, you can extract the ammonia. So you can extract them out separately to each other. Yes, absolutely.
Excellent. And if anyone, I should say that if anyone's looking at these questions and is able to answer them or add comments on them, feel free to jump in and add the comment. Also linked to ammonia, Antonia said, are ammonia recovery plants used also for domestic organic waste liquid digestion, or is it more common to apply them on a wastewater treatment plant? I think she meant industrial organic waste rather than
to be honest, I would say a lot of the experience is in the industrial wastewater streams, and it's now transferring more to the municipal market. So we see a variety of ammonia recovery, whether it's what we've discussed today, using zeolites, using extraction columns or whatever. We see a lot of these or evaporators. We have plants with evaporators on them. So we have experience all these different types of technologies.
I'm not a fan of this destroyer. I think we should be recovering.
I agree.
We've got to get to it.
I'm with you. I think there's a big interest in deammonification, but I think that's just a glorified destruction of nitrogen, just more efficient, using less energy.
That does lead to Tim Jones's question, which was one of the first ones that came up, and I almost overlooked it here. Does recovered ammonia have a lower carbon footprint than conventional fertilizers? That would be a great piece of analysis.
I think if you look at what wastewater treatment does, it's almost the direct opposite of the Haber-Bosch process. So the Haber-Bosch process is where we get maybe 90% of industrial ammonia from, and to put that into context, that's using 5% of the world's natural gas. The carbon footprint of nitrogen fertilizer is anywhere from about 10 to 12 kilograms of CO2 equivalents per kilogram of nitrogen provided. So if you can extract anything, you're displacing the need for that energy and that gas consumption. So anything that can displace fossil fuel based fertilizers is a huge plus.
I suspect Organics might have some information that can feed on that. And
absolutely, yes.
Ben, I think, was it Ben? Tim, we'll see if we can get you a response on that from Organics. Here's a wonderful question that's just come in. Do you observe inhibition caused by melanoidins, yes, either directly, I might need you to explain what a melanoidin is in a minute.
Yes, absolutely.
Do you observe inhibition caused by melanoidins either directly in the AD process or in the downstream processes, such as struvite precipitation, anamox, etc.?
A great question. Yes. So for the audience, melanoidins, what these are? These were first described in the literature in 1912 by Joseph Maillard, and he was looking at food. So when you heat food, when you take proteins and sugars and you cook them together, like when you cook a piece of meat and it goes brown, that brown color is melanoidins. So when you have sludge and you pressure cook it, you're basically doing the same thing. You're cooking the sludge and you create these colored compounds. These colored compounds are refractory, so they can end up in your effluent, but they're largely inert. So they just really pass through the system, so that it can cause a problem in your effluent, in your UV system. But there are ways you can control this. So the production of these colored materials are fundamentally linked to temperature. The higher the temperature in the thermal hydrolysis, the more you produce. So if we're looking at co-digestion, we'll operate at lower temperatures to minimize their production.
Brilliant. Bill, we're bumping up against the hour, so I'm going to thank you for your time. I have to say, I don't know anyone who could have been so technically on the ball in the middle of the night. So absolute all glory to you. That was just incredible. Thank you for your time, and go and get some sleep.
Absolutely, I'll do that. Yeah, thanks very much, and hope it was useful. Yes, take care. Thank you. Bye. Bye.
Now, with that, we come to the end of this week's special broadcast, and I thank all of our contributors, sponsors and partners. In particular, I have to thank Bill, because that was an incredible performance. Those questions coming and getting increasingly more difficult, I thought. Now, if you want to know any more about any of the topics we've discussed today, please let me know. Or if you've got another topic that you think might make a good future Water Actions platform special, then just let us know. Next month, we actually have a special focus on youth in the water sector, and for arguably blatantly obvious reasons, I will not be the host, but instead my colleague, Alicia Sayal, a rising star in the International Water Association, will be the anchor. It'll be held on Thursday, July the 14th. I hope to see you there. Keep asking questions, keep sharing, and keep safe.